Start.
Okay.
Welcome back to our book club for analyzing baseball data with R. We are now venturing into chapter 9, as you can see, called simulation. And what I foresee for us is we're going to simulate a half inning, simulate many versions of a half inning, simulate a baseball season, and simulate many baseball seasons. Where this chapter got started, the author reminds us of the retro sheet data from the 2016 season, and also reminds us that back in chapter 5, we added a few columns to be able to do more advanced calculations to this. So fortunately, with the textbook package, they have that retro add states function to bring us back up to speed from chapter 5's materials that I believe L presented on. At this point, I added this line of code to remind us of these new columns. In particular, we were asking questions like, is there a base runner on first base? Is there a base runner on second, third? What is the new situation in terms of number of outs and where the base runners are? We combine these two to create a new state, and we're also going to keep track of any runs that scored. With those new variables in mind, we define half innings as a augmented data frame that keeps track of the runs for both the away and home teams, gives a half inning ID with the game ID, but also keeping track of the inning, which inning is it, and who's the home team at bat. And then we also are careful about how many outs are in the inning, how many runs were there at the beginning, how many runs scored during the inning, and adding that all up. For my curiosity, I added this line here to note that at this point, we have over 40,000 observations in our data set. That is half innings from the 2016 season. Now, there are some edge cases because of how the baseball games play out. So the authors wanted to talk a bit about what we are counting as meaningful plays. We are retaining observations with a change in state or runs scored. So there might be some strange occurrences, such as a freak injury, where the labeling would stay the same, but otherwise something else happened. When we're talking about bases and outs, we're specifically talking about situations where there was a change in state. We are going to only retain complete innings, which might sound strange because in the bottom of the ninth or the bottom of an extra inning game, we might have fewer than 3 outs. But just to make calculations easier for ourselves, we're going to keep half innings that had all 3 outs recorded. And also of interest, we are ignoring some of the other types of plays, such as steals, caught stealing, wild pitches, and pass balls. That all gets brought up here in the R code. So again, making sure that the state changed or the run scored, making sure that we have all 3 outs recorded. Otherwise, we'll maybe not deal with some of those stranger situations. Out of my curiosity, I added this line of code to assure ourselves that at this point, we are still keeping 96% of the data from approximately 40,000 observations. In the upcoming Markov chains of it all, we need to talk about what constitutes the end of an inning, reading this off. In our definition of new state, we recorded the runner locations where there were 3 outs. At that point, when there were 3 outs, the runner locations don't matter. So we code the new state to always have the value 3 when the number of outs is equal to 3. You can see the states here below the code. So for example, the first one says no base runners, 0 out. The second one says no one on first, second or third, 1 out, etc. What the code is doing is a string replace where it's taking that base runner information and essentially getting rid of it for the three out situation. So when we are in the three out situation here in the bottom right, it's only saying three outs, no need for information about the base runners. And we also note that in the number of observations, this is happening quite often. Sure, I went through all that. Okay. So now what's happening in building what are called transition matrices is that when you count the number of ways that there could be base runners and the three possible outs, there are 24 state labels. In the previous slide, we also tacked on a situation for the three outs situations. So we're going from 24 to 25 state labels, and we could build a transition matrix by going from state to new state and simply using the table function to tally everything. At this point, I wanted to verify visually that this is working so far. So it's too much to show on any one screen, but on the left-hand side, we have the old state. On the top of the columns, we have the new state. And you can see that there's kind of a diagonal-ish pattern for where the most common situations occur. You also see that there are a lot of zeros because in the way we're viewing the baseball half inning, you cannot go backwards. You cannot go backwards from, say, two outs back to zero outs in a half inning. And then there on the right-hand side is our new designation for the complete three out situations as well. In particular, when you think of the Markov chains and some of the underlying mathematics, we have what are called absorbing states. In general, when you have a directed network, an absorbing state means that you have a node where the arrows do not come back out of it. So in baseball, what we're saying is when an inning reaches three outs, it stays at three outs. So the probability of staying there is all 100%. We could take that previous transition matrix, turn it into proportions or probabilities, but also being careful to say that we have that three out absorbing state in the last row. So now in the probability matrix, once again, we have some sense of some diagonal patterns with the most likely probabilities. The zeros, once again, stand for situations where we could not have gone backwards from, say, one out back to zero outs. And in the bottom right, once we reach three outs, this is called the absorbing state, where it stays there 100% of the time. It does not branch back out to anything else. Some other properties, when you have what's called a stochastic matrix, this is called row stochastic. Each row adds up to 100% because you want to keep track of all the possibilities going out from a node. And from time to time, we will need to ensure that this matrix is also a square matrix, same number of rows and columns. These tables and color highlights, I did this in the GT package. If anybody's curious about the code later, I have included that in these fold out code snippets. Rather than looking directly at the 25 by 25 table, it might be easier to see a couple of more concrete examples. So here we display the transition probability starting at this is basis empty, zero out state. No runners, no outs. There in the top right is the most likely outcome where you go from zero outs to one out, still no base runners. The second most likely outcome is that from that zero out, the batter hit a single, got on first base. And now for just a slight mind teaser, how do you go from zero base runners, zero outs to zero base runners, zero outs? Does anybody want to venture a guess?
I assume by getting a run, right? Home run.
Home run.
Yes, exactly. That is a home run situation. So that is saying from that situation, a no base runner, zero outs, a home run was recorded about 3% of the time. Looking at another example, just to continue getting used to thinking about this data, we have a base runner on second base, two outs, which, by the way, might be more likely to happen these days with the extra inning ghost runner rules. From that situation, base runner on second, two outs, the most probable is, of course, just ending up with three outs. What might be of interest is the second most probable is now having an additional runner on first base. So this will include situations where the opposing manager um, asks for an intentional walk or the catcher intentionally called for pitching around the batter and to make it a little easier for the force out. We also see the situation here, runner on second, two outs to no base runners and two outs. And we once again realize this is a home run outcome. In those situations, that happened about 2% of the time. Every once in a while, let me take a pause here and see if there are any more questions or discussions from the book club.
So that last one is two outs, a person on second, and then second and third with two outs. Did it says zero, but I'm curious if that's ever happened.
So this seems like a rare situation where maybe the batter got something like a double, but the lead runner might have been a catcher that was so slow they could not come home.
Hmm. That's interesting.
Mhm.
Hence the 0% probability.
Yeah.
It happens 1 in a million, I guess.
But every once in a while, maybe you send Sid Bream home because you know Barry Bonds is in that field and you just go for it.
Yep.
All right, so we'll dive in deeper into the mathematics now. Uh, in addition to those uh, transition probabilities going from one state to another, maybe you want to also keep track of how many runs scored. And we will eventually go back to talking about the expected runs. So we have a formula for the number of runs scored based on the base runners and number of outs. We'll make a helper function, the number of runners that haven't scored, input a game state, and output the number of runners and outs. So a bit of data wrangling there. But what the textbook authors did very well in this chapter is to be able to build a helper function and then immediately apply it in a map function in the functional programming that you could do in the R programming language. So from the transition matrix, which was 24 rows, 25 columns, I think that's 600 entries, we apply this function 600 times to get a sense of how many runs have not scored. And then we could do an outer product, but with the subtraction arithmetic to get that difference in runs. Now, once again, in the very last row, we just want to shove in our absorbing state for three outs to make sure the overall matrix is a square matrix back to 25 by 25. Now, in interpreting this, I might have some of my words switched, so there might be some errors here. But say on the left, we have a zero base runner, zero out situation. We mentioned that if we go to a new state of zero base runners, zero outs, 1 run had scored, namely the batter hit a home run. If we go from a man on first, 0 outs, to no base runners, 0 outs, that means 2 runs have scored, namely a 2-run home run. Some of these other numbers might not make sense in the same way that I just described. And also the negative numbers are moot in this point because of the old you cannot go backwards in a half inning. So now we want to move on to simulating a half inning. Being mindful that we're going to want to be doing this thousands of times, the authors suggest making a function for this. I wanted to explicitly mention that the inputs are a probability transition matrix, the run matrix that we just saw, and a starting state from one of the 24 situations from the base runners 0, 1, or 2 outs. What this does is actually creates a sequence of states, keeps track of the number of runs scored until we reach a 3-out situation. In the textbook's code, they used a different seed value, which I am guessing was Jim Albert's birthday. I have no particular reason to use Jim Albert's birthday, so I'm going to use today's date. Run this code about 10,000 times once again through the map function to apply the simulate half inning function to our. I'm pretty sure that was supposed to be the probability transition matrix. To our T matrix and the number of runs that are possible in each state. And even with my seed, I got this similar distribution, which is mostly expected. But what is also surprising is that out of the 10,000 simulations, still not a single one of them achieved more than 9 runs scored. So I thought that was kind of odd. For the half innings, we're most likely to see 0 runs scored. That makes sense. And then we kind of have an exponential or Poisson distribution, or I should say an exponential or geometric distribution kind of drop off. So one thing we could do quickly in R is to address a quick question. How many runs are scored on average during a half inning? Taking an average of all this, we get a weighted average. We get about half a run scores during a half inning. Information if you're running some gambling software and such. Now what we're moving towards is simulating the half inning for starting at any point in the inning. And I honestly did not really want the code to run for a couple minutes. I achieved kind of a similar results by reducing the number of iterations by a whole order of magnitude. And what we're making is what's called the expected run matrix for the 2016 season from a Markov chain process. That is a simulation. We're taking this new function, run scored from a state number J, applying that to all 24 possible base out states. It computed the mean up here, so we're storing this as mean run values. And as you can imagine, at some point, compared to our previous representation, we might have also wanted to separate the base runner notation and the number of outs. So a couple of substrings there. So now we could have a runs potential matrix formed here. Let me see if I could annotate this a bit. Need to use orange. All right, so in the top right, if we have a basis empty 2-out situation, the number of potential runs is very small. That seems to fit with our situation. In the bottom left, if we have a basis loaded 0-out situation, the number of potential runs is the largest in the matrix. That also seems to fall in line with our intuition. Sorry. Wait. Looking for the button that just says queer annotations. Zoom makes its software that is good for a laptop computer, does nothing for me on 3 monitors. Anywho, moving on. To understand the effect of non-batting plays, such as stealing, caught stealing, wild pitches, pass balls, on run scoring, we compare this run expectancy matrix with a run 1 found in Chapter 5 using all batting and non-batting plays. So back in Chapter 5, we previously computed an expected run matrix as that ERM 2016 without the Markov chain process. Now, in my ignorance, when I began this chapter, I grabbed the retro datasheet data file from their GitHub page. I did not find the ERM data file here or in the other folders. So that was why I just felt a little lost. I thought to myself,
It's not in there. You have to create it following the steps in chapter 4, I think, or is it 5? I forget which one it is, but yeah.
so I copied the code from Chapter 5 that you had presented previously, saved this as ERM 2016. Admittedly, I'm pretty sure I have an error in my code because
Okay.
once you take the difference of the 2 matrices, we're not supposed to get this many negative numbers.
Right.
And it's not just an issue of the sign, the numbers are probably permutated as well. So at this point, let me just hop over to the textbook's result here. And what's going on is that there's some value in these extra base running plays, such as stealing bases. Whether or not a team wants to rely on those values over the course of a long season is still up to them. So in most situations, notions such as stealing bases has a positive run value, you're more likely to score runs. The exception is that if you have a bases loaded 0-out situation, if you do something crazy on the base paths, you're most likely to hurt your offense. So it's probably best not to do anything there. Moving a bit more into the underlying mathematics, stochastic processes, which is a topic I really like. One of the nice things you could do is when you talk about these transition matrices, especially in the ones that were probabilities, row or column stochastic, if you wanted to talk about multiple iterations, such as 3 plate appearances, all you need to do is multiply that matrix to itself, in this case, 3 times. Starting from the basis empty 0-out situation, the most likely outcome after 3 plate appearances is just simply getting 3 outs. The second most likely outcome is a man on first base with 2 outs. And if you watch a bunch of baseball games, that seems to fit what we're thinking. And just out of curiosity, I looked at the other 22 states as well. Now, when you're dealing with stochastic matrices and you are going through a bunch of theory, such as are there cycles? Is this a directed acyclic graph? Do you want to talk about absorbing states, the number of average visits, and so forth? To summarize some of the calculations that come up along the way, there's this notion called a fundamental matrix. For our purposes, Q itself had to be a square matrix that was row stochastic. So we're going to, in this particular part, not deal with the 3-out states. And you take that matrix, subtract it from the identity, find the matrix inverse, and this is called the fundamental matrix. There were some nice applications that you could do with the fundamental matrix. For example, for starting with the, again, basis empty 0-out situations, we could have this array of the average number of times you're going to end up in the other nodes of our network. Reading this off more succinctly, the average number of times the inning will be in that no base runners, no out state is 1.05. Number of times will be in a 1-out state. The 2-out state with no base runners is 0.6. Of interest is if you start with no base runners and 0 outs, add up all the average possibilities, you get this result here. The average number of plate appearances in and half inning before 3 outs is 4.27. So that was nice. If I could tell you a quick story, one time I was watching a game in Oakland. Our home team athletics were losing in the bottom of the 8th. I told my friend, just out of wishful thinking, Brent Rooker will win this for us. The reason why it was a strange thought is that Brent Rooker was actually 4 or 5 batters away. So you would need people to get on base before him. Suffice to say, in that story, Brent Rooker, walk-off home run. Good game. All right, so visit frequency. You want to get a sense of how often some of these 24 states occur. You can multiply by a vector of 1s. And if you think about what an average is, adding up a bunch of numbers, dividing by however many numbers there are, this multiplying by a vector of 1s does something pretty similar. So you could get the average number of remaining plays from each state. So for example, if there's a person on first with 0 outs, we actually might increase how long the remainder of the inning will be. Whew. I've said a bit in the past 3 sections of slides. Let me go ahead and pause here, see if there are any questions or discussion. Now we are going to further complicate things by taking those 24 base out situations and apply them to 30 baseball teams. Look at how often the teams were in each state in their home half inning. So the home team from the old ID variable is the first 3 letters. And again, keeping track of who's at bat, whether it's the away team or the home team. I'm going to depart a little bit from what the textbook did and actually look at a situation called the noble tiger, which you might have heard of in social media space. I'll type this into chat if you haven't seen this in a while. A noble tiger stands for no outs, bases loaded, ending with team incapable of getting easy run. So it feels great at first. Your team has bases loaded, 0 outs, and then maybe 10 minutes later, they got nothing back out of it. So I wanted to get a sense of how often could this occur, or how often this situation at least has a setup. From the season 2016 data, we're looking at those situations, bases loaded, 0 outs. And I decided to look at this by team. So back in that 2016 season, and oh, by the way, I love when we use these old franchise IDs, because then we could say Anaheim Angels. They had this bases loaded situation 32 times. Whereas in contrast, the Arizona Diamondbacks had this bases loaded 0 out situation only 15 times. That is, again, the start of the inning, not necessarily finishing off the noble tiger itself. But in particular, I wanted to show this situation to say that between the baseball teams in encountering each state, you can have a lot of variance. You can have some teams achieving these states much more often than other teams. Some teams have a lot of offense, some teams have little offense, relatively speaking. So across 24 base out situations times 30 baseball teams, that is now 720 permutations. When you have 720 permutations and talk about probabilities and relatively small sample sizes, you're probably going to induce some variance that you do not want in your models. So for some of these less common transitions, there is much variability in the counts across teams. What the textbook authors suggest and has been done for a while is the smoothing operation, which is essentially a weighted average of the probabilities of going to a state based on the team and the overall league average. What this will do, with a little bit of math here, is say, for example, instead of reporting 32 noble situations for Anaheim, you would actually reduce this number back down towards the mean of the league average. For a lower number, such as the Arizona Diamondbacks, you would actually increase this number back up towards the mean. So loosely speaking, this is kind of a regression towards the mean, but this is done quite intentionally to get, and the sabermetricians experience more reliable predictions. All right, so we're going to eventually move into actually simulating whole seasons. So let's give a little bit of history to this. I personally thought it was of intellectual curiosity to talk about the Bill James log 5 model. I'm probably going to read more about this in the future. But for now, the formula that you see on screen, you can see that the inputs are team A's winning percentage, team B's winning percentage. From your statistics class, you may recognize those individual fractions as log odds that the team is going to win. And those 3 fractions put together is now kind of a weighted mean, or kind of a weighted average of the log odds of winning. So when you put a bunch of statistics concepts together, this seems to make sense. And imagine Bill James double checked the predictive power of this, and I imagine that's part of the reason why he chose the unusual log base 5 when doing some of these computations. However, you might have a situation where you do not necessarily want to plug in team winning percentages. For example, if you're following the current baseball season, you know that Baltimore and Atlanta are arguably underperforming, and you have a hunch that they have more talent on the team than what they are achieving on the field. So the Bradley-Terry model, which has been applied to various sports statistics, instead does a similar calculation, but now you could see that the inputs are some more nebulous concepts called team talent for teams A and B. So we're taking the exponential to counter the log of the log odds. If you do any sort of machine learning, artificial intelligence, you might find this similar to softmax formulas. And if you don't want to get too bogged down with mathematics, what we're going for here is a positive correlation that if a team has more talent, they should be winning more games in correlation. So we'll make a schedule. This takes a vector of team names and the number of games played between the two teams, which will be k equals 9 in this case. With some careful R code, it's just going to do a bunch of permutations to get all the possible permutations. Keep in mind, you also have the home and away teams. And we're going to do this for the 1968 season. In case you're wondering why we're doing this for the 1968 season, the 1968 season was the last one where we only had two playoff teams, the National League winner and the American League winner. That is to say, to make the rest of the code and the exposition in the rest of the chapter easier, we're going to stick with the simple situation where there are only two playoff teams. The next year, 1969, is when they introduced the NLCS, ALCS, the semifinals, basically, where they have more playoff teams. And every time you do that, you get accusations of diluting the playoff field. And that plays in nicely in 1969 when we met the Mets. Anywho, taking the 20 baseball teams from the 1968 season, running them through our make schedule. Also of interest, we group by league, American League, National League, which played right into this group split function. I thought that was pretty clever. Keeping the league separate, so this is also many years before interleague as well. I wanted to double check that the code is working, so I picked on the 1968 Detroit Tigers. You'll notice that the Tigers are aligned and facing off with their opponents, mostly in alphabetical order. Half the teams at home, half the teams are away, and this also verifies that the schedule did indeed produce 162 games. So the 162 is the same denominator that we have today. With that in mind, we're going to compute the probability of which team wins each game towards simulating the seasons. We're going to assume team talent is normally distributed with a mean of 0, standard deviation of 0.2. This is kind of a backwards design. You go take real data and go back to see which number fits here the best. 0.2 seemed to work. So once 10 teams in each league, randomly assigning them a talent level. Now, for the narrative, I'm going to put my finger on the scale, so to speak. Assume that the Detroit Tigers had the most talent and the St. Louis Cardinals had the second most talent. So I applied much higher numbers there for narrative reasons. I might be talking fast just in case we need some time at the end. We attach the talent column to what we had before, and we're bringing in the American League and National League back together again, so we don't need a separate talent column, so we're going to rename those as well. And also, we're assuming that the team talent is independent on the home or away nature. We had the Bradley-Terry model for input talent, output the win probability. So here I offer a sample of 10 situations, being careful that the home team is on the left and the away team is on the right. So that might be backwards from other visualizations. Here, the home team Orioles have much less talent than the visiting team Tigers. So the probability of the home team winning is less than 50%. In the second game, the home team Tigers have more talent than the away team Yankees. So the home team has a win probability of over 50% and so forth. Let me go ahead and take a pause here, see if there are any questions or discussion from the book club. All right, so now in the simulations of the season, what you do is simply have your code go through every game. We're going to use the R binom function to metaphorically flip an unfair coin based on the team talent that we had in the previous data frame. And simply say one of the teams is the winner, either the home team or the visiting team. Looking at a couple of examples, I'll start here on row 3. The home team Tigers have more talent than the away team Twins. The probability of home team winning is greater than 50%, and the home team won. And the Tigers won. In the 4th row, the Cleveland baseball team has slightly less talent than the Tigers. Cleveland at home, so the home team win probability is less than 50%. Nevertheless, it's still possible that Cleveland would win. And we're going to, of course, keep track of this for all 162 games for all 30 baseball teams. Group them by winner, count them up, and just keep track of that. I with a different seed, and also keep once again in mind, I did put more weight to give more talent to the Tigers and the Cardinals. Using the textbook code otherwise, it was of note that you would have to keep in mind tiebreaker scenarios, especially back then when there were only 20 baseball teams. So having ties was a little bit more likely. We're going to say they won the American League or National League if their wins is the highest in their league. And just to make the tables a little easier to read, calling these teams rather than winners. Over in the American League in the 1968 season, the Detroit Tigers had the most wins, getting just barely ahead of the Chicago White Sox in the simulation. In the National League, the St. Louis Cardinals actually tied the Houston Astros in the simulation, but thanks to their tiebreaker, they came out ahead and got to represent the National League in the World Series. In case you're curious, I did double check it. It is Houston Astros. This was actually after the Colt 45s. So we're going to simulate the World Series between the Cardinals and the Tigers. And you know what? I kind of wanted to talk about the narrative a little earlier, but might as well just do it now. 1968, St. Louis Cardinals. On their team, they have famous players such as Lou Brock and Curt Flood, who received MVP votes. But they fell behind in the MVP race because they were behind their teammate, Bob Gibson, who got both the MVP and the Cy Young that year in 1968. Very popular and talented baseball team. What I found curious is in simulating the World Series, which is a best of 7 games maximum, the authors chose to use this R multinomial code. I found that curious because at least if it was me, I would have kept things simple and used binomial distribution and just kept track of things. I'm at the present assuming that multinomial is for situations beyond binary, beyond just 2 outcomes. But you know what? If the sabermetricians have been doing this for years and they are able to simulate the World Playoff Series with 1 line of code, more power to them. Now, in the simulation, with my finger on the scale, Detroit won their 1968 postseason 4 games to 3. So that might come as a surprise. As time progressed, to the casual baseball fan, you probably heard of Bob Gibson, and you might be surprised that they lost a World Series despite Bob Gibson's dominance. I thought it was nice to go back and see who was on the 1968 Detroit Tigers. This player here, Bill Freehan, catcher, 6.9 baseball WAR as a catcher, 2nd in MVP voting, because he was second to his teammate, Denny McQuain, who got the MVP and the Cy Young in the American League. So the American League and National League MVP Cy Young were both shared by the pitchers that season, year of the pitcher. I think it might have been called. So yes, these Tigers came in and at first struggled a bit. Game 1, Bob Gibson won against fellow Cy Young Denny McQuain. Game 4, Bob Gibson won against fellow Cy Young Denny McQuain. The two teams battled it out, and finally at the end, Mickey Loldick outpitched Bob Gibson for the Game 7 win. So yeah, some good history there. And as you can imagine, that's part of the reason why I played around with the numbers earlier, because I wanted to see if I could or emulate that 4-3 outcome in the World Series by plugging in these talent levels. And of course, setting the seed to today's date. All right, so let's see what a little bit more about what the chapter offered for us. If you wanted to simulate, say, that 1968 season many more times, you could wrap everything up in a function. Oh, the sabermetricians might have wanted to tinker a little bit more with the standard deviation of talent, so that could be an input variable. So this simulate 1968 function, there's my code, just the previous code chunks from V4. And once again, compared to the textbook, I decided to only run this 100 times, one fewer in the order of magnitude. I felt that the results were pretty similar. And here's what we mean by the correlation. Talent on the horizontal, number of wins on the vertical. As we suspect, we get a positive correlation. As teams have more talent, they tend to win more games. If we plug in a talent level of 0, they have an average number of wins at 81. And in my further calculations, they're in the orange dots. If I assume more talent for the 1968 Detroit Tigers, as you can imagine, they tend to win more games than average. And then finally, one more question that baseball fans and critics can address is the parity of it all. Is it fair? Can baseball teams reasonably expect to win a championship and a World Series? So what's the relationship between a team's talent and the postseason success? This time around, what the textbook was doing to simulate the 1968 season was a bit more than what I probably was doing in the code that I directly coded. So I went ahead and settled to grab the simulate one season code from the textbook package. We're plugging in that standard deviation for talent, running this just 100 times. And we are computing a conditional probability, the probability of winning a championship given a talent level. And we're doing this over some logistic models. For logistic models, generalized linear model code, the asking did they win the pennant, that is if they won the National League or the American League based on their talent. And this is from our simulation of 100 copies of the season. And in the second model, did they win the World Series based on the talent? For the probability of winning the pennant, I have that in Tiger Navy Blue. And the probability of winning the World Series, I have that in Tiger Orange. In particular, even for a top talent team, and we're maybe thinking of teams like the 2001 Mariners or the 1998 Yankees, even for a top talent team on the far right of the graph there, the probability of them winning their league was still only about 60%, and the probability of winning the whole thing, the World Series, was still only about 1 in 3. Now, any interpretation from there is subjective. Whether or not you think teams like the current Dodgers, Mets, or Yankees can quote unquote buy a championship is still up for debate. And here's at least what some of our early sabermetrician calculations have done so far. That brings us to the end of the chapter. Admittedly, I did not tackle the exercises at this point because I felt there was very much more the same compared to the materials that we discussed so far. But at this point, let's go ahead and talk about this. Thank you.
Cool. Yeah, great job. I thought the chapter was pretty straightforward. I did also, like you kind of said, Derek, I also got a little, well, I don't know if words in your mouth, but I got a little lost in the section about the, what did you call it again? The
Expected run matrix?
No, that part was fine because I did do that before. No, the part about the I minus Q inverse.
Oh yeah, the fundamental matrix.
Fundamental matrix, that's it, yeah. I looked at it a little bit. I mean, I think the way to understand a little bit is to think about what that is in terms of like geometric series. So it's, 1 over I minus Q inverse is the same as like 1 I plus Q squared plus Q all the way to infinity, right? The geometric series. And that's how you're able to treat these things as expectation values. That sum is like taking the expectation value of something. Something to do with like if you keep taking higher powers of Q, eventually you get zeros because you transition out to the absorbing state, but the absorbing state's not there. So those aren't truly stochastic matrices. That's as far as my thought process went. I just said, I don't know. I didn't follow so well when he kept saying like, oh, then we just do this. Then we can, that was 4.27. Like, well, I would have done it differently. I probably would have just done a Monte Carlo simulation and then of the original transition matrix and just seen like how many plate appearances you get on just counting, right? But that
Yeah,
was
I
only,
agree. I think there might have been some interest in keeping some of the theoretical approaches, especially if you're doing this for many baseball seasons or maybe running the simulations for maybe 10 million iterations.
yeah. So that's some of my things to do list is to go up and read up on. I mean, I use Monte Carlo Markov chain all the time, but I've never thought about the fun. Somehow I've gotten away with never having to think about the fundamental matrix. Because I guess because everything I'm doing is kind of simulation, and what I'm trying to say is empirical, not theoretical.
Yeah, exactly. The fundamental matrix just came up in some of the theorems, basically saying are Markov chains even converging towards something?
Right. Whereas, as an empirical person, I assume they converge until they don't. Until something goes wrong. Assume everything's well behaved until it's not, and then be surprised. That's my methodology. But no, I didn't do any of the exercises either. Did anyone else attack them?
Trevin, did some of those tiger names, the player names sound familiar?
Yeah, I saw Al Kaline was a utility player on that team. Great stuff. I might have missed this, but did you say how you came up with the 0.35 and the 0.31?
So if the talent levels are normally distributed with a mean of 0 and a standard deviation of 0.2, 0.35 is nearly 2 standard deviations higher.
Oh, gotcha. Okay.
So I looked at the talent levels that was being prescribed by the simulation code and simply put in higher numbers.
Nice.
Yeah, ironically, the Houston Astros actually did poorly that season in reality, but the simulation had them tie with the Cardinals. I just couldn't believe that happened.
Imagine there's some way to do some kind of like take the actual season's results and do some kind of multinomial regression and find a good set of talents to actually, or back out what the talents could be that would predict the season.
Yeah, and I
That'd be
imagine
a fun
this happens
experiment.
quite often. All those people who seriously make power rankings and preseason predictions, and of course the Vegas odds makers.
Yeah. Cool.